any other transformation, you rotate, then you translate to origin and rotate.
Yeah, but it's using very good. Because this is not do the cross product.
Yeah.
Then like, how to cross product. What the values mean.
I never look at the slides. Never get the point. The start one they could keep the point for the normal. Okay, then get the point. So you use any normal.
There's another question where you also select anything.
This one you mostly choose the kind of normal that is already Z-axis. The third one, like that, choose the point that is already along the Z-axis, then just translate it downwards. Minus Z. No, please intersect the Z-axis. X is Z minus 1, it's like that. This axis, this is Z, right? Yeah, I know. But at least you translate as in one direction only, I don't have two different directions. X, Y, Z,
Just because it's a
Okay, so let's start. So now we move to 3D transformation. Like last week we discussed 3D. So now you can find that actually the basic concepts, the ideas are very similar. So I suggest, for example, when you review 3D transformation, try to review 2D transformation together. Right? So then you can find the basic idea, and also you can learn what's the difference between 2D and 3D. So basically, okay, we just learn affine transformation and its representation, right? And how can we define affine transformation? So at least two ways, right? So one way you define affine transformation in a general setting. So in other words, you don't know whether this affine transformation is translation, notation, scaling, or how those basic transformations are combined to form the affine transformation. So if that's the case, it's good to write or define affine transformation by this 4x4 matrix or 3D equation. So here maybe some students say, okay, I have to memorize that formula. So I don't suggest that you just memorize the formula without understanding. So here what I can say that for transformation, right, the key important is to figure out the relationship between the point before transformation and point after transformation. So if the relationship is linear in x, y, z, so in that case there's only way to write linear function in something times x, something times y, something times z plus constant, right? So then of course you don't need to memorize any formula. So here the understanding is more important. So then, okay, from here, by just linear algebra, you can convert this guy into 4x4 matrix. And this involves homogeneous representation. So you add the fourth component here, and this one is constant. Right? So this is one way to define affine transformation. Okay. So the second approach, okay, we look at some basic transformations. So just as in 2D case, that includes translation, right? And scaling, notation. So, and also, okay, so the pattern of the matrix actually has a very clear geometric meaning. Or in other words, the translation, so how can you define translation? Right? So you have to determine the translation amount. So then where should we put the amount on the matrix? In the last column. Right? So similarly, okay, so for scaling, so how can you define scaling? You have to define the scaling factor, right? So then where should we put that? So we put it on the diagonal. So only for notation, the matrix looks a little bit complicated, right? But try to understand how we derive this formula. And in 2D case, you can find the pattern is kind of cosine, negative sine, sine, cosine. So now you just translate this into 3D case. So when you perform rotation in 3D, then you perform rotation about the line, not the point. So for example, when you perform rotation about the x-axis, so then you can imagine, okay, when this rotation happens, and the x coordinates remain unchanged. So as a result, here should be 1 here and 1, 0, 0, 1, 0, 0. Right? So then the rest part of y and z, just like the x, y in the 2D case. So that's the reason you put the cosine, negative sine, sine, cosine here. Right? So only one point that you have to pay attention is that, okay, when you perform rotation of the y, so the order has to change a little bit. So as a result, the minus is not put here, it's put here. Right. So the others are almost the same. Right. Okay, besides those basic 3D transformations, we also have some reflections, right? So the reflections, so we have more situations. So at least we have 7 standard situations. And the reflection slope point, reflection slope line, reflection slope plane. Right. So you can define a fine transformation by composing those basic or simple transformations. So basically, the question here so can be classified into 2 types. Right? The first type say, okay, we use this general formula. So you try to figure out the correspondence between the object before transformation and the object after transformation. So specifically, you pick up some point pairs. And so you know the x, y, z and x prime, y prime, z prime. So you just substitute it into this formula. You can build a system of linear equation in those coefficients. And those coefficients actually are unknown to be determined. Right? So that's the first approach. And the second approach, so you should be recognize the pattern of those questions. The second type of the question like that, so you are required to perform a sequence of the transformation. And those transformations are, for example, translation, rotation, scaling, reflection, because those are relatively simple and geometrically intuitive. Right? So then you say, okay, how can we write out those kind of matrices? But of course, we can easily make the situation complicated. Just introduce non-standard situation. So if you have a non-standard rotation, non-standard reflection, then you say, okay, we have to do some pre-process. Then try to figure out what kind of pre-process we should perform first to make the non-standard situation into standard. So the logic, the concept, I have there. Right. And in the lecture, okay, I give a very special case. I show you that we can perform at most 2 rotations to make a vector line with z-axis. And this actually is the most complicated situation as the pre-process. Because the translation as a pre-process is very simple. Right. So we will see the application of that process later or in the tutorial question. Right. So now we go through the tutorial question. So you just ask yourself, so what kind of question is this? So earlier I mentioned there's 2 types, right? So you should be recognize the type of the question. Then you know, okay, how can we go ahead? Right? So if you, for example, read this question quite along, right? Be patient to read that line by line. Then you can find some keywords there. For example, rotation, like reflection, like a scale, right? So those are actually keywords, and those keywords are hidden that. So here you are required to perform a sequence of those simple transformations, right? So we have to go to the second type, right? Because for first type of the question, usually you have no idea whether the transformation is a rotation, translation, or scaling, and so on. Right? So then, okay, for this kind of question, as I always recommend, right, and also I mentioned last week, so don't try to figure out or try to find the matrices for all those transformations immediately or in one step, right? or don't try to mix up those individual transformations. So you just ask yourself, okay, how can we define this rotation? Okay, so what kind of matrix or what kind of matrices for this rotation? So that's the first step, right? So for the rotation, we have three standard situations. Then you check whether this is standard or not. If yes, then you can write the matrix immediately, right? So now you see, okay, here rotation is about axis, and this axis goes to the 2 points, right? So those 2 points are not on the x-axis, y-axis, z-axis. Why? Because there's no zero there, only 1, 1, 1, 1, 1, 5. So it's non-standard, right? So then say, okay, you can perform some pre-process, right? So of course here you can use the approach I give in lecture to do that. As I mentioned in the lecture, I give a very general approach, right? So here you have a line, you can always make that line align with the axis. But in this situation, actually, if you draw the line, you can find this actually is a very simple situation. You don't need to go through the rotation. Why? Because you say, okay, here for P1, P2, they share the 2 same coordinates, x and y. So both x, y coordinates are 1, 1. So what kind of line is this? So they have same x, y coordinates. The only difference is in z. So this line actually is parallel to z-axis, right? So if you draw the figure, right?
Because it's really same line as z-axis.
So actually for this kind of 3D or even 2D problem, right? So involve some geometry or transformation. So it's possible just sketch some reference first, so then you can find the. So here, for example, you draw the. So you draw 3 optional lines. So for example, is this x, this y, this is z. So you can find where the point P1 is somewhere here. And P2, for example. Right, so for example, if this point has coordinate 1, 1, 1 and this 1, 1, 5, so this line is parallel to the axis. So then you can get some idea, right? So how can we make this rotation be the standard rotation? A very straightforward approach. Just make this line be z-axis. How can you do this? Just a translation. For example, if you move P1 to the origin and this line becomes z-axis, so no need to perform any rotation. So that's very simple, right? So we get the idea. Okay, for the first rotation, you perform some translation first, right? Make the P1 be the origin. Then do a rotation about z-axis. Then translate it back. So eventually, this rotation involves 3 transformations. And we know the matrices for all those 3 transformations. So then the first one is done. Right. Then you go to, okay, the next required transformation is a reflection. Right. So what kind of reflection is this? It's about XY plane. Then this is a standard situation, right? So then you can write the matrix for this reflection immediately. So then this is done. Then you go to next. So what next? Okay, scale, right? Scaling and the uniform scaling, and you know the scaling factors are 2, right? Sx, Sy, Sz are 2, right? So then you have to ask yourself whether this scaling is standard or not. Then it's a scale with reference to a point with coordinates 1, 2, 3. So this is not origin. So that means this scaling is not standard scaling, right? So how should we do? Okay, it's the same. So we just do some pre-process. Make the reference point be the origin. Then you have a standard scaling, right? So how can you make this one be origin 0, 0, 0? By a translation. The translation amounts are -1, -2, -3. So you can make the x, y, z coordinates all 0. Right? So then you can find, okay, for a scaling, also involve translation, the standard scaling and translation. So then this is done. That's it. So the next, okay, just put those matrices in a block order. Since we perform rotation first, so those matrices for rotation should be on the right. And then let's come to the rotation. You do this pre-process first. So this matrix should be on the rightmost. Then rotation matrix on the in the middle, and this post-process on the left. Right. Then on the left is a reflection, and left then this guy, this guy, this guy. Right. So then actually now the thing becomes simple. What remains is just filling those data into these standard matrices. Right. So as a result, you see, okay, the red one is for rotation, and the white matrix for reflection, and those yellow three matrices are for skin. Right? So then just figure out, okay, so what's this translation? Translation, okay, here. So this translation, right? So 1, 1, 1, 1, that's the identity matrix. So now you introduce the translation, put a -1, -1, -1, and those three guys are the translation amount. Right. Then go to the rotation. Then you see, okay, when rotation, pay attention to that. This is a rotation about z-axis. So this one is 1. So what remains is filling this guy. So here is a cosine, negative sine, sine, cosine. Right. Then see, okay, what's the rotation angle? So go back to what's the rotation angle? Over 2, right? Pi over 2, that's good. So then, okay, should we use a pi over 2 or negative or minus pi over 2? Then see the rotation direction. So counterclockwise. So you just use a pi over 2, right? So here you can find that this is cosine pi over 2 gives 0. This is a minus sine pi over 2 gives 1. Similarly, this is sine pi over 2 0. Right. So then translate back. This is also translation matrix. Now the translation amounts are 1, 1, 1. Right. So then this guy is a reflection slope xy plane. So then you ask yourself, okay, what's the property of the reflection slope xy plane? Imagine here this is the xy plane, the point above will become point below. So xy coordinates remain same, and z become minus z. So that reason here only z become minus z. Xy should be same. Right? So then similarly for peripheral translation and the scaling factor are 2, 2, 2 for uniform scaling and translate back. So then that's it. Right? So if a single matrix is required, then you have to multiply all those matrices. But in most situations, okay, you are not required to give a single final matrix. Then just leave all those matrices in this way, and that's it. Right. So this, of course, defines a general affine transformation. And this transformation is defined by translation, location, scaling, and reflection. Alright, so this is one typical type of the question in this module and also in previous module. Right. So if you say check some previous year's exam paper, you can find quite similar question here. So here, just as I said, so the logical approach actually is not so difficult. So just, be patient, try to figure out the matrix or matrices for each required transformation. Right. So sometimes the pre-process may make you a little bit difficult, but then just should be okay. Analyze what kind of pre-process you want to perform to achieve your goal. Right. So question 2 actually is another type. Okay, it belongs to another type. Right. So as I mentioned, actually the first type. So here we require the general definition of the affine transformation. So here I like this kind of approach. So we by 2 questions we can say different types of the question. Right. So okay, first one just perform some analysis to test whether you understand the formula or definition for the affine transformation. The second, okay, apply the knowledge to perform some calculation. Right. So here say, okay, how can we define arbitrarily affine transformation. So as I mentioned, okay, so that case you have to figure out a 4x4 matrix, right? And in that 4x4 matrix, the last row is constant, 0, 0, 0, 1. So what you have to figure out, what you have to find, are just those coefficients, A, B, C, D, and something. So how many coefficients are there? So there are totally 3 rows, and each row you have 4 elements. 3 times 4, 12 coefficients, right? Or see here we have 12 unknowns. Right? Then you see, okay, so if you choose a 1-point pair, 1 point from orbit before transformation, another point after the transformation, and each point pair give you 3 equations, 3 constraints, right? So then understand those are the facts, right? So now you ask yourself, how many equations, how many constraints do you need to determine those unknowns? You have totally 12 unknowns, right? So okay, by the math, linear algebra, so if you have n variables, then we need at least n equation, right? So now you need 12 equations, and each point pair gives you 3 equations. So we need 12 of 3. We need a 4-point pair in general, right? So in other words, if you want to determine a 3D affine transformation, then you have to pick up 4-point pairs, and those 4-point pairs give you 12 equations. Then you can solve for those 12 unknowns. So here, so you have to perform some analysis a little bit, use the definition of a general affine transformation, right? So now, okay, we just apply this idea to this special situation. So you have 2 objects, one is a cubic cube, defined by 8 vertices, 8 corners. So this cube is transformed to a prism, and this prism also is bounded by 8 vertices, and you know all the coordinates. Right. And also you are told, okay, this prism is obtained by transforming this cube using some affine transformation. So that means there does exist some affine transformation. Right? So what we have to do, just try to find those coefficients. See, then you can pick up some point pair. For example, first point, 0, 0, 0 will be mapped to minus 1, 0, 0. And similarly for those guys. So just choose some point pair to set up a set of the equations. Right? So then you can eventually find the value for the A, B, C. So here you can find the approach is also the similar as the approach we did for 2D situation. Right? So I hope you will be also you are familiar with this kind of approach, and the remaining part actually is quite a tedious work, right? So now say, okay, we just give the general definition. For example, here I use x, y, z for the coordinates for the point before transformation, and x star, y star, z star as the x, y, z coordinates for the point after transformation. So this is a general formula, right? So then we choose a 4-point pair. For example, you choose a 0, 0, 0, minus 1, 0, 0. This is 1-point pair. So, and this point pair should satisfy this affine transformation. Like why? Because this point comes from the original point. Right? So that means 0, 0, 0 are just x, y, z in those 3 equations. And the minus 1, 0, 0 are x star, y star, and z star. So just substitute in here, you get 3 equations. Right? So similarly, you can choose second point pair, for example, second point pair. So 1, 0, 0, and this is mapped to 2 minus 2, 0. So that means 2 minus 2, 0 are x, y, x star, y star, z star, and 1, 0, 0 are x, y, z. Right? So then you substitute here, you get another 3 equation, right? So you continue this, right? Continue this. So if you choose those point pair properly, then you can set up 12 equations, then you can solve for those coefficients. So once you find the value for those 12 coefficients, you can find this 4x4 matrix, and this 4x4 matrix define a affine transformation, right? So So just as I mentioned, so the remaining part actually does a tedious computation. Right? The idea concept at the very beginning. Right? So that involves the definition, whether you really understand the definition of the fine transformation law. So here, just as I always mention, emphasize, right? So when we study this course, or even other courses, the same. So the basic idea, the concept is more important. Then you can work out the detail, right? Don't just pay attention to detail and forget about the original thinking, right? So that if you just memorize some particular formula, if you don't understand, this does not help, right? So this is another type of the question in this kind of area, or this kind of topic, right? So now let's look at some more complicated example, right? So usually those situations are non-standard situations, So now, okay, here the first is just a background. So that means we use the column vector as that's our default assumption. So use a column vector to represent the point. So use XYZ or XYZ1 to represent right. So we are required to define the matrix or matrices, which can define a reflection about the plane. So reflection is a simple transformation, right? And also we have already derived 7 matrices for standard situation. So now you are required to find the matrix for this special reflection. And these reflections are about the plane, not the line, not the point, right? So, but the plane is defined by this equation. So then you can find, okay, this plane is not XY plane, not YZ plane, not ZX plane. So that's a very general situation or non-standard situation. So just this equation or this plane complicates the question. If this is XY plane or a plane parallel to XY plane, then the situation is actually very simple, right? So now, okay, what's the idea? The idea is similar. Okay, so we want to do some pre-process, make this plane be the XY plane, for example, right? So then you do the reflection to XY plane. So to determine the pre-process, so first you have to understand, okay, what kind of plane is this, right? So if you get some idea about the orientation, about the position of this plane, that help you to figure out the pre-process, right? So usually, okay, this involves some math skill. That's actually not the computer graphics course, right? So for example, I give you an equation. How can you figure out the orientation or this location of the plane, right? How can you do this? So usually, okay, so if you actually choose some point on the plane, it's difficult to draw on 2D plane, right? So you don't have this 3D information, 3D sense, right? So you must choose some point with some reference that you can see, okay, relative relationship. You can feel the spatial information or depth information, right? So here is highly recommended that choose some point on the plane. Meanwhile, that point, for example, on the x-axis, y-axis, z-axis, because when we sketch those guys, you have sketched the coordinate system first. So you have reference there already, right? So that gives some hints. So now, for example, if we draw, it's up to you. So for example, if I draw like x, y, and z like this way, so now you have reference here. Say, so if the reference is this one, so where's the plane? Right. So how can you do this? As I said, okay, we try to find some point on the plane. Meanwhile, the point is on the x-axis. So what's that point? And that point is the intersection between x-axis and this plane, right? So then say, what's the property of the point on the x-axis? So for any point on the x-axis, you can find, okay, it's y z